So PIN is basically a class of neural networks with physics-based constraints. It kind of bridges your ML, your data-driven models, and the physical reality. And the seminal paper which made it famous was Mazia Raizi's paper in 2019 from Professor Karniadakis' group in Brown University. But it traces its history all the way back to I.E. Lagares, who had published the first paper on how you could use artificial neural networks to approximate PDE solutions, and he had compared it with traditional finite element method. And now here you can basically have a standard pin which is continuous in space time, or you could have other different neural network backbones which could be also continuous in space time, or continuous in space but discrete in time, or discrete in space time, both, right? So it could be a bit combinatorial here. The major masala that makes it physics informed are the physics constraints which embed your ODEs, PDEs, or some sort of algebraic equations, or constitutive laws, or embed additional symmetries of the underlying system into the model. And you obviously have the database constraints, which are your observation data or simulation data, partially or fully observed cases, or your boundary conditions, initial conditions, and you have your system parameters as well. So in certain cases, which we will actually consider moving forward, is what if you were to infer a system parameter given some partially observed data, right? So which becomes an inverse problem. So input, just to revise the flow, input coordinates, then there's a feed-forward neural network. At least for this purpose, we're going to look at only feed-forward neural network, no other specialized backbones. Feed-forward neural network, there are going to be some outputs which go through the automatic differentiation pipeline. Again, you compute your data-driven losses, you also compute your physics-based losses, which in case of fluid dynamics, they are often your continuity and momentum conservation equations. In case of electromagnetism, they're going to be your Maxwell's equations. If it's climate, it's going to be your entire Earth system model or your ocean models. And along with that, you're going to have your carbon dioxide forcing and sea surface temperature forcing, etc. And then if it is traffic flow problems, you again have a set of OD optimal flow or optimal transport equations which govern traffic flow. So you could have varied domains in which a pin can be applied for. It all matters on what your inputs, outputs are, how you're going to actually model the system, and how are you going to use this automatic differentiation box to get to those constraints and enforce them through another loss component. And the combination of this, a weighted combination of this in some cases, is what you're going to use and finally optimize to calibrate the parameters of this neural network. The key benefit of pins so far have been that they work really well for spatiotemporal function approximation given limited and sparse data. And the best part of a pin here, at least in the feed-forward neural network setup, is that your collocation points or your temporal spatial coordinates can be sampled from anywhere in any arbitrary domain. So it doesn't have to be of a specific shape or a structured format. So it could be from an unstructured grid, structured grid, any randomly distributed grid, set of collocation points as well.